They're functions of the form y equals a times b raised to the x power. And exponential functions come up a lot in modeling real life behavior of things. And can anyone think of something? Well, we won't talk about that yet. Okay? But they're
I won't say
yes.
anything to screw it up.
So they're functions of the form y equals a b raised to the x, where a cannot be equal to 0, otherwise you wouldn't have anything there. And also a cannot be equal to oops, that's wrong. B cannot be equal to 1, otherwise you get a straight line, because 1 raised to a power is just what? What's 1? And that's why if you plug in 1 in here, you end up getting a flat line, which you may have discovered, okay, because 1 raised to any power. So B can't be equal 1. And also, that B is, they kind of have this wrong in the book. The absolute value of B has got to be greater than 0, okay? Actually, should we have some number? No, B has to be greater than 0. So B has to be a number bigger than 0. Can't be a negative number. If we have a negative number, we put it in front of with the A, okay? So B has to be a number bigger than 0.
So why can't it be 1 then?
Why can't it be 1? Because if it is 1, what's 1 to the second power?
1.
What's 1 to the third power?
1.
1. So what you end up getting, if I plug in numbers, I just get a straight line that doesn't look like an exponential function. So this number has to be bigger than 0. Yes?
Shouldn't it be bigger than 1?
Doesn't have to be bigger than 1, because you might have discovered when it was 0.5, what happens to that function? Can anyone remember what happened when b was 0.5? What did that graph look like? It goes like this, right? If b is like 0.5, that's what you should see. If b is a number bigger than 1, then it goes up like this. And this, as we'll learn, is called exponential decay. That's like radioactive decay, or the price of your computer going down over time, or the speed of your fastest time as you get to be an old man running the 100-yard dash or something like that. That's exponential decay, okay? Whereas exponential growth is when things go up really, really fast, okay? And so if it's going downhill, that's still an exponential function, but it's a decay function. And if it's going uphill, then it's a growth function, okay? The way you tell that something is an exponential function is with a table of values, is like this. So say I'm doing my table across, where this is x and this is y, and I'm going to plug in numbers over here, like 1, 2. Anyway, let's move on. So an exponential function, if this is x is 1, 2, 3, 4, 5, 6, okay? And I have some numbers like 2, 4, 8, 16, 32. What would come next? 64. And they ask you, is this an exponential function? Is this an exponential function? The way you tell with a linear function, so linear functions make lines. Exponential functions make curves that go up like that. And the way you tell is with an exponential function, maybe some of you discovered in that activity, what am I doing to this number to get the next number? Multiplying by 2, right? So to go from this number to this number, I'm timesing by 2, times by 2, times by 2, times by 2. So with an exponential function, you're multiplying, okay? And that is called the common ratio, I believe. Okay, don't worry about it that much, okay?
Well, I put it in there just in case.
Okay. It's called the common ratio. I don't think that's in your homework, but is 2. That's your multiplying factor. if I couldn't figure out in my head what I'm multiplying by just looking at it, what's the opposite of multiplying? Dividing. So if I divide this number by this number, what do I get? 2. If I divide this by this, what do I get? So to figure out what I'm multiplying by, all I have to do is take the next number and divide by the previous number, okay? And if it's a linear function, so they say, is this an exponential function? And they give you this, 2, 2, 2, 2, and then they have x, y, 1, 2, 3, 4, 5, and then they have these numbers, 3, 5, 7, 9, 11. Is this an exponential function?
No.
Why not? Who said no? Why not? Jasmine?
Because it's hard to find.
Yeah, you're not, go ahead, Orion. Yeah, it's hard to find an even number. What were you going to say?
You're not multiplying.
What am I doing?
You're adding.
Good. Okay, this one is changing by 2 each time, right? When it's changing by the same amount, that's a linear function. So if I graph these points, this one makes a line, right? It's going to go through 1, 3, 2, 5, 3, 7, 4, 9. It's going to look like this. Whereas this one, it's going to go 1, 2, 2, 4, 3, 8, 4, 16. You see the difference? That one's going up way, way, way faster. Okay? So exponential functions, they go up or down by multiplication. Linear functions go up or down by addition or subtraction. So I made a nice note here. So and the reason we like exponential functions is because they can model real life things that are going on. Okay? For instance, suppose there are 30 flower beetles left undisturbed in a warehouse. The beetle population doubles each week. Okay? And the function f of x equals 30 times 2 to the x gives the population after x weeks. How many beetles will there be after 56 days? So in an exponential function, unlike in a linear function, the variable is up here. Okay? So they want to know how many beetles will be there after 56 days. And this is the initial amount right here. Remember that last problem in last night's homework where it has something sub-zero, a little zero on the bottom? That means how much you're starting with. Right? So how would I figure out how many beetles there are after 56 days if it doubles each week? Notice this is days, and this is weeks. How many weeks are there in 56 days?
8.
There's 8. Okay? So what am I going to do with that 8, Orion?
Do you raise 30 to the power of 8?
No, you plug in 8 up here. You see? Okay? And so if you start with 30 times 2 to the 8, it's because it's doubling 8 times. So just to show you what this is, 2 to the 8th. Anyone know what that is? We know that 2 to the 5th is 32, 64. What is it? Oh, what?
150.
150.
Wait.
That doesn't sound right.
156.
Is it 150?
It's 256.
256. That's what I thought. Okay. So this is 30 times 256. Can someone do that on a calculator and see what you get? 30 times 256. Can you do that, Grace? 76. 7. So 7680. Like that, 7,680 beetles after 56 days. Okay. So when things grow exponentially, they grow very, very, very fast. A lot of times. Okay. Let's see if you can do this one. This is a U tribe. Okay? U tribe. Get this one right, I'll give you a bonus point. Initial population 20 rabbits, whipples every half year. The function of f of x equals 20 times 3 to the x gives a population after x half-year periods. How many rabbits would there be after 2 years? Okay, so give that one a try. It should be pretty easy. And ready, go. Okay. And I think he was correct that it's 20 times 3 to the 6th power. So what I would do, since exponents go first, I would do 3 to the 6th first. And if you do this, say that again, Owen. 43,740 rabbits. Okay, that's a lot of rabbits, and that's after only six doubling times. Right? Yes.
I got 14,500.
Yeah. Oh.
That's probably.
I think that is that's on 14,500.
Yeah. 14,500.
Yeah, that sounds right. 14,580 rabbits. All right. So that's a lot of rabbits.
Mr. Leader, I think we should just explain again quick about how you got the age and the time factor and how it's 3 years is because there's 6 half years.
Because it says X is the number of half years,
Here, listen
right?
up, you guys, because I think several of you have this.
And so there are 6 half years and 3 whole years, right? And so that's why the number 6 goes in here rather than 3. All right. And then on your calculator, if you had a calculator, all you have to do is, I'm not going to show you. Let's just go back. All right. So it's just you go 20 times 3, and you should have a little button that looks like that. 3 to the 6th power. Usually that's what it looks like. There is a y dx key or something like that. 14,300. All right. I want to talk about a couple more things here. So what if I wanted to graph? So sometimes I'll ask you to graph exponential functions. And you can do that pretty easily by making a table of values. So graph y equals 3 times 2 raised to the x. And you do it just like you're doing a table for any type of graph. I'm going to make an x. I'm going to make an x and I'm going to make a y. X, y. And then I'm going to put some graphs, make some lines here. I'm going to pretend that it's to scale. Okay? And I'm going to plug in the numbers. Usually I want to start with 0. And then go 1, 2, 3, maybe 4 just for kicks. All right? And so when x is 0, who can tell me what y is in this exponential function?
1.
It's not 1. Who said 3? Very good. How is it 3, Sage?
Because since 0 is the exponent, won't that just cancel out?
It's 3 times 2 to the 0, right?
Yeah.
Which is what? What's anything raised to 0? 1, which gives you out 3 times 1, which is 3. So this is what? See that? Okay. Now I'm going to move over. 3 times 2 to the 1. What's 2 to the 1? 2 to the 1 is 2 times 3 is 6, right? And then, now you can think about it, what am I multiplying by each time? You don't even have to plug in the numbers, because what's my multiplier? What am I multiplying by each time? It's right here. 2. So what's this number going to be? 12, right? What's this number going to be? What's this number going to be? 48, right? You understand how I got that? Because I figured out what I'm multiplying by, and then all I have to do is multiply the previous number. Okay? So then when I graph them, you got to be kind of careful of your scale with exponential functions, because these things go up very, very, very fast, right? 0, 3 starts here. 1, it already jumps up to 6. And then 2 to 12, I'm already kind of out of here. You know? And so what this graph looks like, if I start at 0, it's a very steep curve that looks like this. And actually what happens, we didn't explore with any negative values, but it doesn't get, you don't get any negative numbers, you just get numbers that look like that. So that's what y equals 3 to the 2x look like. The other way I could go backwards is by dividing by 2. What's 3 divided by 2? 1.5. So if I went to -1, I would be at 1.5. If I divided that in half, I'd be at 0.75. If I divided that in half, and divide that in half, and divide that in half, that's how I get some of the numbers going that way. Follow that, Victor?
Yeah.
Sure you did. Okay. So then here's something else that you're going to see, and it's just a table. It says computer mapping software is just an application. And in an area to view it in more detail, the function 100 times 0.25 to the x models the percent of the original area. The map shows that presuming graph the function. So I'm just going to show you that sometimes exponential functions, instead of going uphill, they go downhill. If this is your area, and this is your zoom factor, okay? Software allows you to zoom in on area. The function models a percent of the original area. So if at 0, I would get 100, okay? So this is the point 0, 100. And then as my zoom factor goes up by 1, I'm only seeing 25% of my original area. Okay, so after 1 zoom, I get that. After 2 zooms, I'm at 6.25, and so on and so forth. So this one, hi there. We are looking for Sawyer. You need to go. Sawyer,
Okay.
Sawyer, you're not in trouble. Just you have an appointment or something. Okay? All right. So this one, if I graphed it, is actually going downhill. Okay? You guys remember that original problem I gave you about the pennies?
Yes.
So let me just show you this. Look, the penny problem. If your parents gave you a penny on the very first day of a month, right, and say I double that every day, after 1 day, so this is an exponential function, which looks like it actually is y equals 2 to the, you're going to start with 1 penny, right? And then you're going to double that every day. So so it's actually going to start 2 to the x. So the first day is the 0th day. So how many cents am I going to have on the 0th day? 0, right? On the 30th day, well, actually on the 31st day, since you're starting when x is 0 on the very first day, so on the 31st day, what's that exponent going to be? Is it going to be 0 or is it going to be 31? It's going to be 1 less, right? Because on the first day, x is 0, right? And so this number is going to be 30. Let's do 1 times 2 to the 30th power. Can someone do that on their calculator for me and see what that comes out to be? Go ahead. 2 raised to the 30th power. See what you get, Jeff.
That's a lot.
Okay. His number is, this is pennies, remind you, so it's not that much, okay? His number is 10737373737471824. We gotta throw some, well, first we have to put, for it, that's pennies, right? So I'm gonna divide that by 100 and make that cents, right? So now I'm in dollars, because I moved that way. And then I'm gonna move this way. And then I'm gonna move this way. So on the 31st day of the month, your parents would have to pay you $10,737,418.44. Okay? And that's not including how much they paid you the previous day, which is half of that, right? So the day before you get $5 million. The day before that you'd only get $2.5 million. The day before that you only get $1.25 million. Okay? So you guys tell your parents, Will you just do the, I'm willing to work for a penny a day. All you have to do is double it every day for a month, and I'll do whatever you ask, okay? They might be coming after
No, I don't think
Anyway.
they realize how much that was costing until it's a bit too late.
I know.
And after they-
So, I really don't think we're gonna have time for the dynamic exploration activity. Maybe we'll do that on Friday.
Think about
I need to think about it.
We
Here,
have to do it Friday. It's a good thing.
we'll do it Friday. So this, you're gonna start on right now, good? Which is homework page 457, 58 through 50, every other even. You may start, good?